Okay, so I think we're recording. We're good. There shouldn't be any more technical difficulties, hopefully. So this is where we left off on Wednesday, all the way back last week. So we were talking about transposes, and then we were about to start talking about permutations and what happens when you transpose a permutation matrix. So just as a reminder, all you need to know about transpose matrices at this point in time is that they take your matrix, and what they do is they switch the rows and the columns. So what I mean by this is if we have this initial matrix, we'll call it A. The first row is 2, 3, 1. If we take the transpose of this matrix, it's going to give you a new matrix where instead the first column is going to be 2, 3, 1. So the first row of this matrix becomes the first column of the matrix after you apply the transpose. Then similarly, the second column is obtained by taking the second row of your initial matrix, and you just like flip it horizontal to the vertical, right? That's all that's going on so far. And so in terms of a description with respect to the entries of your matrix, the transpose of your matrix, the ijth entry, is just going to be the jith entry of your initial matrix that you had. So that was illustrated here, where the 2, 1 entry of your initial matrix becomes the 1, 2 entry of your new matrix. So all you do is just switch the indices. Rows become columns, columns become rows. And so that has an effect on the dimensions of your matrix as well. We have 2 rows and 3 columns. We're now going to have 3 rows and 2 columns after the transpose. So that's what's going to be important. I mean, we're not going to go too deep into like what's going on with transposes for like applied to every single matrix ever. But we're going to record a couple of properties. The most important one, or where we left off yesterday, or on Wednesday, was that if we have 2 matrices, A and B, such that you can multiply them together, so the number of columns of A is equal to the numbers of rows of B, then if you take the transpose, what happens is you just switch the order of B and A. So it's the transpose of B times the transpose of A. So it switches the order, similar to what we saw with inverse matrices as well. In the past, we saw that if you do A, B inverse, it's the same thing as doing B inverse times A inverse, right? It switches the order of the multiplication. So the same thing occurs for transpose matrices, or when you apply the transpose to a product. And I don't have this written down in this PowerPoint or this presentation, but you should also take note, and this should be intuitive, that if you do the sum of 2 matrices and you apply the transpose, is this the same thing as doing the transpose of A plus the transpose of B? And this should be pretty intuitive in that if you took the transpose of these things, like all you're doing is, again, just switching the rows and the columns and then just of A and B, and then just adding them together. So you can see this as well. The reason why I'm saying is on one of the problems of the review, you have to use this back. So I thought I would record it. But this should be pretty intuitive. Okay, so that's where we left off on Wednesday. I have the formal typed up proof. And so continuing just talking about more properties of the transpose and what happens with transposes, we have the following corollary from the previous proposition that says that if A is a square matrix that is invertible, then it means our transpose is going to be invertible as well. And then more specifically, we have that the inverse of the transpose is going to be the inverse of A transposed. So you're really just switching the order in which like T and -1 show up. So again, the inverse of the transpose is going to be the inverse transposed. And so the proof of this really isn't going to be so bad. So if we have that A is invertible, what this is going to imply is the following. So it means there's going to exist a matrix A inverse such that we have that the identity is equal to the product of these 2 matrices. And so all you have to do is you just take the transpose of both sides of this equation and it'll maintain equality. So if you take the transpose of the identity, this will be equal to A times A inverse transposed. And then if we transpose the identity, what would we end up getting? Like, what's the resulting matrix? Yeah. Anytime you do a diagonal matrix or like a matrix with only entries on the diagonal, when you do the transpose, you just get the same matrix back. So the identity transpose is just the identity. Meanwhile, applying the previous proposition, so this proposition right here, we know that the transpose switches the order of the multiplication. So this is going to give you that A inverse transposed times A transposed is equal to the identity. Right, so this is really what we're looking for, right? We showed that if you multiply A transposed with this matrix right here, you end up getting the identity. And then similarly, if you just switch the order of this initial multiplication, if you did A inverse times A, you would also get that the identity is going to be equal to A transposed times A inverse transposed. And so what this implies is that the inverse of A transposed is the inverse of A transposed. So this implies that the transpose of A inverse is equal, or the transpose of A inverse is equal to the inverse of A transposed. Right? If you want to show two matrices are invertible or the inverses of one another, you just show that their product is the identity on both the left-hand side and the right-hand side. So we can conclude that we have this equation right here. And so this is going to be something you'll have to do on the exam, is determine like when two matrices are invertible. How you do this, you just multiply them and see they give you the identity. Okay, any questions about any part of this proof? Okay.
So for the invertible, you gotta multiply them both ways then?
Yeah, like later on we'll see that it suffices to just do it one way. But for now, like do both left and right to show that they're inverses to one another. Okay, so then I have the more like of the fancier typed up proof. Yeah, and then the key observation was that the transpose of the identity is just going to be the identity again because it's a diagonal matrix. Okay, so really I think the last kind of thing you need to know for the exam on Friday is this notion of a symmetric matrix. And I guess maybe there might be a problem on orthogonality as well. So these two definitions are going to be important. You'll need to know them. So the first definition, we say that S, so assuming S is an n by n matrix, we say that S is going to be symmetric if we have that the transpose of S ends up just being equal to S itself. So we've already seen an example. The identity matrix is symmetric because if you take the transpose of the identity, you just get the identity. And then we also have another definition involving the transpose. So a matrix Q is going to be said to be orthogonal if we have that the transpose of Q is going to end up being its inverse. So there's going to be special matrices that if you transpose those matrices, you end up getting the identity, or you end up getting their inverse back. And so an important class of orthogonal matrices are going to be permutation matrices, which is something that we've seen in the past. Those are matrices where you just switch the order of the rows of the identity matrix. So we'll prove later on today that permutation matrices are going to always be orthogonal. But first, we'll just look at an example. So for this example, we want to show that the following permutation matrix is going to be orthogonal. So how you would determine that this is going to be an orthogonal matrix is you're going to take the transpose of this matrix and then you're going to multiply it with P, and you want to see if it ends up giving you the identity back. So the first thing we do is we're just going to let P transpose, like we're going to compute the transpose of P. So this, we start off with a 3 by 3 matrix, so the transpose is going to be 3 by 3 as well. And so how I usually do the transpose is I just look like this is the first row, so it's going to become the first column of the transpose. right? First row becomes the first column. Second row becomes the second column. And then we have that the third row becomes the third column. So the rows become the columns, columns become the rows. And so now if we were to multiply these two matrices together, we want to get the identity matrix back out. So we have 0, 1, 0, 0, 0, 1, 1, 0, 0, multiplied by 0, 0, 1, 1, 0, 0, 0, 1, 0. If you multiply these two matrices together, this should be a pretty familiar task to you at this point in the semester. The first entry will be the first row dotted with the first column. So that's just going to give you a 1. First row dotted with the second column is going to give you 0. First row dotted with the third column is going to give you 0. And if you just continue, like the next one will be like second row dotted with first, second, third column will give you 0, 1, 0. And then the last row is going to be the third row dotted with the first column, second column, and then third column for the entries. And that'll give you 0, 0, 1. So it gives you exactly what you want. You get the identity matrix back out. So it's good in that direction. And then you can also check, like you also have to show that if you do the transpose of P times P, you would end up getting the identity matrix. And it's an easy check once again. If you switch the order of multiplication here, you end up getting the identity matrix back. So this too, you can check, ends up giving you the identity. And so what this implies, or what we were able to show, is that the transpose of our permutation matrix P is really just P inverse, right? Any questions about this example? Yeah, so that shouldn't be too bad, I don't think. And at this point, when I'm asking, like, if a question regarding symmetric, like, transposes and symmetry show up on the exam, you're really just going to be using the algebraic properties of the transpose I mentioned before, namely that the transpose distributes over sums and it switches the order of multiplications. That's mostly what you're going to need to know for the exam. Okay, so the next thing we're going to do, like we looked at a specific example where we saw that the transpose of a permutation matrix is just the inverse. We're going to show this always ends up happening. And the main observation that allows us to make this conclusion is really just in these 3 sentences. So the important things about permutation matrices is that they're like the rows of these permutation matrices are just taking the rows of the identity and switching the order in which they occur. So what this means is that each row of permutation matrix is going to have exactly 1, 1. Every other entry is going to be 0 on the row. And then no 2 rows are going to have a 1 in the same column as one another. And so these, or really this one observation, like this is the key observation right here, is going to allow us to conclude that the transpose of permutation matrices will always end up giving you the inverse. So what this proof looks like, and I'm just going to look at, it's not like the most important proof in the world, so I'm just going to kind of say it in words based off of like what's been typed up. So the key observation is we're just going to look at what ends up happening when we multiply these two matrices, first in terms of what happens on the diagonal entries of our new matrix, and then what happens when we look at entries off of the diagonal. So for this proof, we're going to assume that P is a permutation matrix, and we're going to look at the product of P with P transposed. And so first, we're going to be looking at the entries on the diagonal. So that means we're on like, this is the ith entry of your matrix. So something of the form like 1, 1 or 2, 2 or 3, 3 or something along those lines. And so by definition of matrix multiplication, this entry of the product is equal to this sum that we have right here. So you should be thinking that the row of this matrix is fixed, and we're going from like one entry, like one column to another. So the only thing that varies in the sum is going to be the columns. So you'd be thinking like we're going along the row of the first matrix. And then this term right here tells you that the column is going to be fixed, but we're going down the rows. So it's like we're going like down the rows of the second matrix. So this is like really capturing what's happening on with matrix multiplication. This is the dot product of the ith row of the first matrix with the ith column of the second matrix. So I don't think on the exam I probably won't make use of this, but it's good to know for the rest of the class. And so what ends up happening is we have that this is the ith kth entry of P times the k ith entry of the transpose of P. By the definition of the transpose, you can switch the order of these indices. So that way it becomes PIK. Like really this, maybe this is like obvious for everyone, but I just want to write it out. Anyways, like this PKI transpose is really just the same as PIK. And so you can rewrite this sum as just being PIK squared. And so due to the fact that each row has exactly one row or one, and no two rows have one in the same column, this is going to imply that every time you take the dot product of the rows and the columns, at least on the diagonal entries, you're always just going to get 1 plus 0 plus 0. So you end up just getting 1. Again, this is because we have exactly one non-zero entry on each row of the matrix. And so then what ends up happening or going wrong when I is not equal to j is we have the exact same setup, except now the number of like the ith row could be different from the jth column. In fact, we're assuming that this is different, like these two numbers are different. And so after applying the transpose, what you end up getting is you get P, like the I kth entry of P and the j kth entry of P multiplied with one another. And so really, like we're on the exact same column, right? We're in the kth column for both of these matrices, but we're on different rows of the two matrices. And so the key observation is that the rows cannot have a 1 in the same column because it's a permutation matrix. Every single column can only have a single 1 in it, right? Otherwise, it wouldn't be a permutation matrix. So you get a dot product of the following form. You'll probably get something of the form of like 0 times 1 plus 0 times 1 plus 0 times 0 or something. And so you end up just getting 0. And so this would end up proving that the product of these two matrices end up giving you the identity. You have on the diagonal, you always get 1s, and then off the diagonal, every other entry is going to be 0. So it has to be the identity matrix. So this is how you would formally prove a statement of this form. And again, proofs aren't the most important. Like, I'm not going to ask you to prove a lot of things in this class. I think it's more of like computational focus. But it's good to know this stuff, right? It's like building mathematical ability. Okay, so it shows transpose or permutation matrices are always symmetric or orthogonal, I mean to say, like they're always orthogonal. And then what I wanted to close at least section 2.7 on is the following. So we're going back to this LU factorization we were discussing before. And I think I talked about this a little bit on Wednesday, but for the LU factorization, there's kind of like an important thing we were skipping, or an important fact we were skipping. And that's the fact that you can't perform like row switches or switching of rows in the process of the LU factorization, at least like once you get started. And so sometimes like you're carrying out the LU factorization and eventually you'll get a row that doesn't have a pivot in the right place. Like you're not going to get something that's upper triangular. And so before you do the LU factorization, it means you have to multiply by a permutation matrix and then do the LU factorization. And so I just wanted to go through an example where this ends up happening. And again, it's going to be pretty rare that this ends up occurring, at least in this class, but it's good to go through at least one example. Okay, so this is the example we're going to be looking at. The main summary is that the matrix that's given here is not going to admit an LU factorization as is. So what you need to do is you need to find a permutation matrix P such that if you multiply A by P, you can then apply the LU factorization. And then it wants you to find L and U such that PA is equal to L times U. And so how things can go wrong, I can probably squeeze it on this slide, at least like this initial step. Where things can go wrong with finding an LU factorization is if you're in the second row and you don't have a second pivot, like a pivot in the 2-2 entry, or you're in the third row and you don't have a pivot in the 3-3 entry. So what I mean by this is if we wanted to eliminate this 2 right here, what we would need to do is we would multiply by the elimination matrix given by, so it's just the identity, but then you would have a -2 in the 2-1 entry. So this signifies that we're taking row 2 and we're subtracting from it 2 times row 1. So things are going to go wrong after applying this matrix multiplication. So the first row remains the exact same. Then you would have 0 here, and then you would have 4 minus 4. So you end up getting a 0 in the 2-2 entry of your second row, which is going to be an issue. And then you have -6 plus 1 will be -5. And then the third row remains the exact same. So the issue is that we have this 0 pivot right here. It would be much better if this were the third row instead of the second row. Because like as it stands now, like we're not going to be able to have a good LU factorization, right? Like we don't have something that's upper triangular. So we have the 0 right here. And so what this means, so let me say, like this is bad, like this is not good. And so how you can see based off of this matrix, well, maybe I should ask you. So if I wanted to have a valid matrix that I can apply the LU factorization to, which 2 rows should I end up switching? Yeah, you just want to switch these 2 these 2 rows with one another. And again, the intuition is we have a pivot or a non-zero entry here. And so we'll see what ends up happening. So what we want to do is we want to switch the second and third row. And so what this means, so now we have to think like what's the corresponding permutation matrix going to be? So how we get the permutation matrix of interest is you just take the identity matrix and then you just switch the second and third rows of the identity matrix. So the first row will be the exact same as the identity matrix, but then the second row is going to be 0, 0, 1. And then the third row is going to be 0, 1, 0. So we took the identity matrix and we just switched the second and the third rows with one another. So now if we considered P times A, this is just going to be, the effect is you just switch, what this will do is it will just switch the second and third rows of A. So this means that the first row will be 1, minus 2, 3. And then the second row of this new matrix will be the third row of the old matrix. So it'll be 2, 1, 0. And then the third row is going to be the old second row. So this is 2, minus 4, 1. Okay, and so now we want to apply LU factorization to this matrix instead and see what happens. And so we already went through one of the steps before. We had like this -2 in the 2, 1 entry, and this really is going to correspond to the following. So we can instead, actually, let's just do things in order. So I'll just multiply. Let's just get rid of this matrix or this entry here, like this 2 here. So if we were to do that, it would be, you get the matrix 1, 0, 0, -2, 1, 0, and then 0, 0, 1. This is multiplied by PA, not just A. So this is 1 minus 2, 3, 2, 1, 0, and then 2 minus 4, 1. Multiply these things together. First row stays the exact same. Second row is what's going to end up changing. So you get 0. You get 4 plus 1, which is going to give you 5. Then you have minus 6. And then this is going to be 2 minus 4, 1. So I got rid of this entry right here. And there's no issue, right? Because now we have that the 2, 2 entry is going to be non-zero. So we don't have any issues with the pivots or anything like that. And then what we're going to do next is we want to get rid of this entry 2 right here. And we already saw before what ends up happening. Like this is kind of a repeat of what we've already done, except now the elimination matrix has a minus 2 in the 3, 1 entry instead of the 2, 1 entry. But really the effect is going to be the exact same. So this is 0, 5 minus 6. Oh, and then yeah, we're just doing the multiplication. So if you multiply these things, it'll be 1 minus 2, 3, 0, 5 minus 6. First two rows stay the same. And then you end up getting 0, 0, and then 5. Or minus 5. See, now everything ends up working out. You get an upper triangular matrix. And so this is going to be our U. And then to finish the problem, you just have to determine what your L is going to be. The L is just going to be the product of the inverses of your elementary matrices. So this is going to be the inverse of this matrix multiplied by the inverse of our second elimination matrix. And again, the inverses of elimination matrices are always easy to compute. You just switch the sign. So this is going to be 1, 0, 0, 2, 1, 0. Oh, I'm like insane. So this would be 1 instead. Like that's mix up the order of the 1 that shows up. And then this is going to be 1, 0, 0, 0, 1, 0, and then 2, 0, 1. And then if you were to multiply these two things together, you end up just getting the following matrix. So it's going to be 1, 0, 0, 2, 1, 0, 2, 0, 1. So that's how you find what the L is going to be. So this is just following what we were doing in class on Wednesday. I think we went through an example. But again, the interesting part of this problem is we had to apply the product of a permutation matrix before we had to go through with the LU factorization, due to the fact that we had this 0 pivot. You can also think like if we were then to apply, if we were to continue with this example and we multiplied by minus 2, you would end up getting this 0, 5, minus 6 in the third row, and it wouldn't be upper triangular, so it'd be a problem. So okay, and you can test to see, like if you multiply L with U, you end up just getting PA back. Okay, any questions about this example? Okay, yeah, so on the exam, you'll have to find an LU factorization of a matrix. You might not, I don't know if I'm gonna make you do like the permutation stuff before, but you might, so it's good to know this. Okay, so that's everything you need to know for the first exam. So that ends chapter 2. So we start with chapter 3. This is kind of like, this is where linear algebra really begins, I would say. So this is like, we're going to start talking about vector spaces. Everything we've been doing in this class, we've just been doing pretty much on like the real number line, or like an R2, R3, or Rn. So it's always been with real numbers. But we're going to start talking about like the more general idea of a vector space. And so I guess like the importance of understanding vector spaces is it's going to allow us to generalize a lot of the nice properties we know about the real numbers and apply it to a more like wider range of spaces that can that show up in mathematics. just by noting like what are the most important properties of the real numbers. Okay, so this first slide is really just summarizing what I just said. So one general example of a vector space that we've seen extensively throughout this course so far has been Rn. We've been explicitly, pretty much like exclusively working with Rn throughout the entire class. That's going to change with this section. And so Rn just consists of all column vectors with n real valued components. So really these are just like n by 1 vectors pretty much. So it's pretty much, it's like the nicest space to work over. It's what you're most familiar with. And so what we've seen so far is that this vector space Rn is governed by two primary operations. You can add vectors with one another, which is entry by entry. And then there's scalar multiplication on the vectors, where if you do a scalar times a vector, you multiply every single component of the vector by whatever the scalar is given by. And so, I mean, these are two really general operations that we're performing. Like there's a number of different ways in which we can add a bunch of spaces together, and a number of different ways in which we can multiply scalars to certain mathematical objects. And so that's what we're going to be exploring in this section, is really just vector spaces or spaces that are different from Rn, but are also very similar to Rn. So for instance, maybe an intuitive example of a vector space would be, instead of taking real entries or real numbers, we instead use complex numbers instead, and we perform the exact same operations. So this is a common vector space, Cn. So this is like n tuples, or really n by 1 vectors with entries consisting of complex numbers. So that's kind of an intuitive one. If you look at the collection of all 2 by 2 matrices, this too is going to end up giving us a vector space, because you can add matrices together, and then you can also apply scalar multiplication to matrices as well. So that's going to be an example, or an important example of a vector space. And then you can also start looking at functions as well, like spaces of functions. So another important example of a vector space is going to be denoted in the following way. So if you see this, this is going to be the collection of all functions on the closed and bounded interval from 0 to 1 to R, such that f is continuous. So you can add functions with one another, and you can multiply functions by numbers. So it makes sense that would be able to define a vector space based off of just looking at functions instead of looking at numbers explicitly. And so what a vector space is, so these are just like intuitive ideas in terms of like, well, we can add them together and we can multiply them. But you need a little bit more to define a vector space. So it's like kind of a long definition. But really, like, a vector space is going to be a collection of vectors denoted by this bold V, together with the operations of vector addition and scalar multiplication. So exactly as I was saying before. And it has to satisfy the following 8 rules. So these 8 rules, you should be thinking in terms of, I mean, you don't have to memorize all of these, I would say. Like, I'm not going to ask you to like prove by going through like 8 different like criteria to determine a vector space, but you should be thinking in terms of like whatever ends up holding true for like addition on the real numbers should end up applying to vector spaces as well. And then whatever ends up happening when you multiply like a vector of real numbers by a scalar should end up applying to this vector space as well. And so what you have to have is that addition is commutative, so the order of addition doesn't matter. You should have that addition is going to be associative, so you can do x plus y plus z. It should be the same as doing first x plus y and then adding z afterwards. There has to be an additive identity, so if you do x plus 0, you should end up getting x back. So you have to show on the vector space that there exists like an identity, an additive identity. You also have to show on the vector space that for every single vector x, there exists a unique vector minus x, which is an additive inverse. Meaning if you do x plus minus x, it has to be equal to 0 for all of your vectors x. There has to be an identity scalar. So if you multiply x by whatever your identity is, on your field of scalars, you should just end up getting x back. And it's like kind of tiring just reading these out, but there's only 3 more. So it's this, next is like the scalar multiplication is associative. So you can do C1 times C2 and then multiply by your vector x. It's the same thing as doing C2 times x and then multiplying by C1. And then the other are just distributivity. So scalar multiplication distributes over vector addition, and then addition of scalars distribute over a vector. Okay, so again, it's a lot of different properties, but all of these properties are familiar from work in Rn, right? Like these are just the basic, like in order for things to work out well, you kind of have to have that these properties end up holding. Otherwise, like just adding numbers or multiplying numbers can be really messy. So you need things to happen to, these things to happen to have some form of like coherence. Okay, so generally, at least like on quizzes or on an exam, I'm not going to ask you to prove something is a vector space. But what I'm probably going to do pretty often is I'm going to ask you to prove that something is going to be a subspace of a vector space. The reason why I'm going to ask this is, I mean, the questions are, it's a more interesting question first and foremost, but you only have to prove 2 different things. So a subspace of a vector space is going to consist of a subset of vectors of your initial vector space, and it has to include 0, such that for any vectors v and w in the subspace and any scalar c, you have to have that v plus w belongs to the subspace. So subspaces are closed under addition. That's the main takeaway here. And then you also have to have that if you multiply any vector in your subspace, it's again going to end up being in the subspace. So this means that every vector in the subspace has to be closed under scalar multiplication. So in a way, like using under the 2 operations we have, nothing can escape the subspace. If you start with 2 entries or 2 vectors in your subspace, you always have to be able to add them and again remain in the subspace. And you always have to be able to multiply those vectors by a scalar and still be in the subspace. And we'll see later, this is really going to be the same thing as just saying that all linear combinations of vectors in your subspace are going to remain in your subspace. So subspaces are just subsets of your vector space that are closed under linear combinations, is what we'll see later on. And so we'll just finish class by going through an example of what it means to show something as a subspace. And it's a more simple example of a subspace, but we'll look at more complicated examples later. So for this example, we want to show that the following collection of numbers in R3 is going to be a subspace of R3. And so everything's pretty typical, right? The only thing that's unusual is we're always letting z be equal to 0. And so if you want to show that this is a subspace, you first need to show that it's closed. P is closed under addition. And so how you would do this is you'll take 2 arbitrary elements of P and then add them together, and you want them to remain in our subspace P, or what we want to show as a subspace P. So elements in P look like the following. So this is like x1, y1, and then 0, right? P just consists of all numbers in R3 such that the third component is equal to 0. So x1 and y1 are both real numbers, and then you have 0 here. And then we just want to add it to another element inside of P. And so if you add these 2 numbers together, you end up getting the following. You're just going to have x1 plus x2 in the first component, and then y1 plus y2 in the second component. And then the third component, you just have 0 plus 0. So that's going to be 0 again. So you can see that this is in P. Oops. So this lies in P. So that means that P is closed under addition, right? You add these 2 vectors and you end up with another vector inside of P. And then you do something similar with respect to scalar multiplication. So you can probably already see what ends up happening, but just writing out in detail, we want to show it's closed under scalar multiplication. And so you just take any C that's in the real number line, and then you just multiply it by an element inside of P. So it can be X, Y, 0. So this is going to be equal to CX times, or CX in the first component, CY in the second component, and then C times 0 in the third component. This is just equal to CX, CY, 0. And you can see it lies in P again. So this is an easier example, but I just wanted to illustrate what's going on with showing something as a subspace. Okay, any questions about this example? Okay, so I guess, so on Wednesday, we're going to be doing an exam review for the entire class. So I'll just be going through problems on the review I posted on Friday. Then Friday is the day of the actual exam. So it won't be another week until we talk about subspaces again. But if you have any questions, feel free to reach out to me. And I have 2 hours of office hours today as well.